We are familiar with the definition of logarithm. Logarithm is the inverse function of an exponential. So 2 to the power 3 gives 8. Because of that, the logarithm of base 2 of 8 is 3. Logarithm has some basic properties which can be deduced in the same way as this example. Also, logarithm has many other properties, such as this, that we can take a power to the front of the logarithm. In this video, let's get familiar with the sum of logarithms, difference of logarithms, with the rule that we can take the power out, that is the logarithm of a power, and then the last rule where we can change the base from A to B. We just need to divide by some factor. What's the logarithm of base 10 of 5 million? We can write the argument as 5 times 10 to the power 6. Now we have here a logarithm of a product, and our formula tells that we can express this as the sum of the logarithms. Now, what is this number here? To what power should we put 10 to get 10 to the power 6? The answer is 6. Now we can put this number into calculator and calculate the approximate value. Let's simplify this expression. We have the sum of logarithms, that's the logarithm of the product of the numbers. It seems here that we can cancel out with 11, and we can also cancel out by 3. So we get something like this. We can write the argument, the variable, in this way. Because 1 divided by 100 it's 100 to the power minus 1. It's 10 to the power 2 to the power minus 1, which gives 10 to the power minus 2. By using our formula, we can change this product of numbers, its logarithm into the sum of these logarithms, and the later logarithm here, the logarithm and the 10 would cancel out and we get -2. We could put this number into calculator and get some approximate value. We can simplify this expression. We can combine the logarithms and if we notice that this factor here is equal to x minus 1 times x plus 1, we can cancel out these factors and we can cancel out one pair of y's. So we would get something like this. Here is our next formula. If we want to simplify this expression, we can express it as a difference of logarithms the later logarithm here is a logarithm of 10 to power 4, and here base 10. Here we can cancel out the logarithm and the 10 to get 4. So we get -4 plus logarithm 10 of 3. We can now solve the previous problem in a different way. We can factor the numerator and denominator here. For example, in this way. Here we can cancel out the 3's already. By using our formula, we can express the first logarithm as a difference of logarithms. Similarly, the second one we can express it in this way. Now the 3 and the 10 to power 2 were both in the denominator, so we got two terms with a minus sign. Now we have here log 10 of 11 and minus log 10 of 11. These will cancel out. And in the last logarithm, the logarithm and the 10 we can cancel out and we will just get 2. So we can express the result, for example, as the form log 10 of 8 minus log 10 of 3 minus 2. We got the same result as before. From this formula we can get some special cases. If x is equal to 1, we get that log a of 1 over y is log a of 1 minus log a of y. What is this number here? What power should we put to a to get 1? Any number to power 0 is 1, so this is 0. So we get the formula logarithm of an inverse number is minus logarithm. We can also write this in another way. It tells that we can put the minus 1 in the front. By using this rule we can calculate these numbers. At first, what should be the power of 2 so that we would get 8? 2 to power 3 is 8. So log 2 of 8 is 3. Now we could find the other number in the same way, or we can change the 1 divided by 8 to 8 by using a minus sign. So our answer is minus 3. Let's use the next rule to calculate some logarithms. If we have the log 2 of square root of 8, we can express the square root as power 1/2. We can shift the power 1/2 into the front of the logarithm to get 1/2 times log of base 2 of 8. We know that this number here is 3, so we get 3 over 2. Similarly here, we can take the log 2 of 2 and log 2 of third root of 8 separately. The first logarithm is just 1. We can write the third root as power 1/3. The power comes to the front and we get something like this. This is 3. So 3's will cancel out and we will get 1 plus 1, which is 2. The last rule expresses the change of base. We can change from base A to base B. We just need to divide by some factor. For example, we might calculate the log 100 of 1 million. We can change the base into log 10. We just need to divide by log 100 of 10. There is a mistake here. we need to divide by the same kind of logarithm. Okay, so now we could think that 1 million is 10 to power 6 and 100 is 10 to power 2. So we could divide here, we could cancel out these logarithms and tens, and we would get 6 over 2, which gives 3. We could have got the same answer by seeing that 1 million is 100 to power 3. We would get 3. The real use of this rule is that we can change logarithms to different base. So if we, for example, like some base very much, it's enough to use logarithms of that kind. So, for example, logarithm of base 10, we can express it by using the natural logarithm. So if you, for example, happen to like the natural logarithm very much, you can express all the logarithms in base 10 by using the natural logarithm. Let's calculate the approximate value for the log 2 of 1.1. We can express both of the logarithms by using the natural logarithm. So we did a change of base, and now I happen to remember that natural logarithm of 2 is about 0.7. I remember another fact that the square root of 2 is about 1.4 and 1 over square root of 2 is about 0.7. So the latest quantity I can express about as 1.4 times the natural logarithm of 1.1. For natural logarithm we have this approximation that natural logarithm of 1 plus x is about x when x is small. So natural logarithm of 1.1 is about 0.1. Plugging this to our equation, we get about 1.4 times 0.1, which gives 0.14. You don't need to calculate these kind of things in this course. You can just remember that changing the base of logarithm is easy, and if you like some specific logarithm, for example the binary logarithm or the natural logarithm, you can do all of your tasks by using that. If you are solving some equation, it does not matter which logarithm you would take here. If you take the logarithm of base 5, you would get after some steps that x is let's calculate nicely. Let's take the logarithm of base 5 from both sides. Let's take the power x out from there. This gives that x is this number. If here we would express both of these logarithms by using some logarithm of another base, for example, we could use the natural logarithm. The end result is that these factors will cancel out, and we see that while calculating some fractions of logarithms, it does not matter which logarithm you are using. So when you are taking logarithms on both sides of some equations, you can use any logarithm whichever you like.